After studying this module, you shall know and understand the meaning of heteroscedasticity, learn the reasons of occurrence of heteroscedasticity in regression models, analyze and interpret consequences of using OLS in the presence of heteroscedasticity. Let us understand the concept of heteroscedasticity. We would begin with a beginner's perspective. Suppose a student becomes interested in gender inequality and its negative effects for development of capabilities of women, their freedom of choice, and human development in general. She collects data on the so-called Gender Inequality Index, GII, from UNDP's Human Development Reports for 152 countries for the year 2013. GII is a composite measure reflecting inequality in achievement between women and men in 3 dimensions: reproductive health, empowerment, and economic status. It can take values between 0 and 1, lower numbers reflecting greater gender equality. From her data, the students finds that the mean GII is 0.3754, median is 0.3850, and standard deviation is 0.1899. The student interprets the distribution of GII to be fairly symmetric since mean is almost equal to median, with wide variation since standard deviation is almost half as large as the mean. She notices that countries in her sample are very heterogeneous with stark variations in socio-economic dimensions. If this student wishes to develop an econometric model in order to determine the factors influencing GII, she is most likely to encounter the issue of heteroscedasticity. One of the most common violations of the classical linear regression model in cross-sectional data consisting of heterogeneous units in the sample. An econometrician's perspective, what is heteroscedasticity? To understand the meaning of heteroscedasticity, let us recall the homoscedasticity assumption of the classical linear regression model. Homoscedasticity refers to a phenomena where the error terms in the population regression function are identically and independently distributed with the mean 0 and equal variance sigma square. For a 2-variable population regression function, which is denoted as yi is equal to beta 1 plus beta 2 xi plus mu I, where I is from 1 to n, this is our equation number 1. Symbolically, homoscedasticity implies that variance of mu I given xi is equal to variance of yi given xi is equal to sigma square, where I is equal to 1, 2, 3 to n. This is our second equation. This equation 2 reflects the dispersion of error terms around their mean 0. It is also a measure of dispersion of the data values of the dependent variable around the linear regression line beta 1 plus beta 2 xi. The constant value sigma square implies that this dispersion is same for all observations on x. The violation of this assumption is known as heteroscedasticity. It is basically a phenomena where the stochastic random or disturbances exhibit a non-constant conditional variance. Symbolically, heteroscedasticity implies that variance of mu I given xi is equal to variance of yi given xi and is equal to expected value of mu I square is equal to sigma square, where I is again equal to 1 to n. This is our equation 3. Heteroscedasticity basically is a result of data generating process that draws disturbances for each value of the independent variable from distributions that have different variances. It also implies that dispersion of the dependent variable around the regression line is not constant. Heteroscedasticity usually arises in cross-sectional data where the scale of the dependent variable tends to vary across observations and in highly volatile time series data. It is less common in other time series data where values of explanatory and dependent variables are of similar order of magnitude at all points of time. A standard manifestation of heteroscedasticity is that the spread of actual y values around the linear regression line will not be constant. Also, the plot of regression residuals against, say, the predicted y values will exhibit some characteristic pattern instead of being random. Let us illustrate with the following example. Example number 1, which is on annual salaries of professors and years since they completed their PhD. Now, figure 1 shows the scatter plot of annual salaries against years since PhD of 222 professors from 7 US universities, which are US Berkeley, UCLA, UC San Diego, Illinois, Michigan, Stanford, and Virginia for the year 1995. The source of the data is Ramu Ramanathan 2002. It can be seen that the spread of y values around the average straight line relation is not uniform. The variance initially increases, then decreases. As Ramanathan points out, the salaries of recent PhDs are very competitive in the job market, and hence salary differentials are not expected to be high. Salary of tenured professors might vary depending on their productivity and reputation. After a number of years, salary increases tend to stabilize, and hence the variance is likely to reduce. Scatter plots like these point towards an underlying heteroscedastic regression model. A log quadratic regression in which log of annual salaries is regressed against a constant years since PhD and squares of years since PhD for 222 observations yield squared residuals presented in figure 2. We can see that the squared residuals are first increasing, then decreasing, a pattern consistent with the behavior of annual salaries depicted in figure 1. This residual plot is characteristic of underlying heteroscedastic population disturbances. The plan of the module is as follows. In the next section, we present a discussion on some of the common reasons why heteroscedasticity is likely to be present in regression models. Section 4 explains in detail the structure of heteroscedastic variances commonly used in the literature. Section 5 highlights the serious consequences of using ordinary least squares or OLS for estimation and statistical inference in heteroscedastic regression models. The module summary is presented in the last section. So let us understand why does heteroscedasticity arise in this section 3. There are many reasons why error variances in regression models may be heteroscedastic. Let us look at these causes in the following discussion. Heteroscedasticity as an anticipated part of the model. If the observations in cross-section are related to homogeneous units of different sizes or scales, the assumption of a common disturbance variance for all observations is often violated. Consider the following examples. First, suppose that the profit of a firm at a given time depends on research and development expenditures. Since large firms engage in higher research and development expenditures, which are associated with greater risk, one can expect a variation of profits around the mean for large firms to be greater than the corresponding variance for smaller firms. Therefore, the variances of the error terms in such regression models, even after accounting for variation in firm sizes, are expected to be greater for large firms than for small firms. Similarly, consider regression models for household expenditures. Households vary in size as measured by the number of family members and the level of income. Since households with large income have more discretion and choice with respect to consumption, households with higher income will have greater dispersion around a regression in which slope coefficient beta 2i varies across observations. In the household expenditure example, it means that the effect of a given change in income on household expenditure will be different for low income and high income families. To illustrate the concept of heteroscedasticity, let us assume that the slope coefficients vary randomly across some fixed value beta star. Then we can say beta 2i is equal to beta star plus epsilon I, or yi is equal to beta 1 plus beta star plus epsilon I into x1i plus mu I, or yi is equal to beta 1 plus beta 1 star xi plus epsilon I xi plus mu I, or yi is equal to beta 1 plus beta star xi plus mu I, where mu I now is equal to epsilon xi plus mu I. Now, equation 4 shows that the error term mu I will vary with xi and will have unequal variance. So, heteroscedasticity due to data issues is now discussed in this section 3.2. Many times we have monthly or quarterly data on an economic variable, but we need to work on yearly data. Finding averages is a common method for aggregation. Heteroscedasticity can be generated as a consequence of data aggregation. The second reason could be that choice of a wrong scale. Sometimes heteroscedasticity arises because variables are measured on a wrong scale. Measuring the variables in logs as percentages or as ratios reduces the scales in which the variables are measured. A homoscedastic disturbance term in a logarithmic regression responsible for proportional changes in the dependent variable may appear to be heteroscedastic in a linear regression because the absolute changes in the dependent variable will be proportional to its size. Let us discuss the presence of outliers. Now, outliers or extreme observations in the sample make the homoscedastic assumption difficult to maintain. The next reason could be we have explanatory variables with a large range or skewness in their distribution. If the data on an explanatory variable has a large range of values, it may lead to larger variance of error terms for larger values of the explanatory variables. Similarly, skewed distribution tend to generate heteroscedasticity. Heteroscedasticity due to specification errors. Here also we may have different possibilities. The first is the omitted variables case. If a researcher omits a relevant variable from the regression model, the effect of this variable will be captured by the error term. It will appear that there is a systematic relation between the disturbances and some exogenous variable, and the variance of the error terms will not be constant across observations. The second possibility is non-linearities. The same problem occurs if a researcher estimates a linear relation instead of a quadratic or any non-linear model, and the error term of the linear model captures the effect of non-linearities. Wrong functional form could be another possibility. So if a linear function is fitted to an underlying quadratic or logarithmic true model, or in general a wrong functional form is chosen, then the disturbances appear heteroscedastic. Now let us try to understand ordinary least squares in the presence of heteroscedasticity. If the error terms in a k-variable regression model are heteroscedastic and ordinary least square is still used as the estimation procedure, then there are serious consequences for estimation, interpretation, and statistical inference. Consequences of ignoring heteroscedasticity is discussed now. Look at the effect on finite sample properties of OLS estimators first. The OLS estimators of the regression coefficients beta j hats, where j may change from 1 to k, are still unbiased in the presence of heteroscedasticity. That expected value of beta hat or beta j hat is equal to beta j, where j is equal to 1 to k. The second point we want to make is that the ordinary least square estimates will be inefficient. They will no longer have the minimum variance in a class of unbiased estimators and hence are not blue, which means variance of beta j hat is greater than or equal to variance of beta j tilde, where beta j hat is the OLS estimator that ignores heteroscedasticity and beta j tilde is another linear unbiased estimator, but estimator that mainly explicitly takes heteroscedasticity into account. The conventional estimator of the variance of the error term sigma square is biased. This is our another consequence of heteroscedasticity. It basically means that expected value of sigma hat square is not equal to sigma square, where sigma hat square is equal to sigma mu I hat square upon n minus k. The fourth consequence is that the conventional formula for the OLS estimators of the variance of regression coefficient is wrong. The OLS estimators of the variances and covariances of the regression coefficients are biased. Another consequence is that the conventionally constructed confidence intervals are no longer valid. Similarly, we find that the T and F statistics based on the OLS regression do not follow the T and F distribution respectively, and hence standard hypothesis tests are invalid. Let us understand the effects on asymptotic oblique large sample properties of all these. First effect is least square estimators of model parameters are consistent. That is, probability limit of beta j hat is equal to beta j, where j is equal to 1 to k. The second is the ordinary least square estimators are inefficient and not blue, even asymptotically. The third effect is the conventional estimator of the variance of the error term sigma square is inconsistent. That is, probability limit of sigma hat square is not equal to sigma square. Another effect is that the OLS estimator of the variances and covariances of the regression coefficients are biased, hence hypothesis tests are invalid even in large samples. Let's now look at the effects on forecast. Forecasts based on the ordinary least square estimates will be unbiased and consistent but inefficient. About the proof of properties of OLS estimators in the presence of heteroscedasticity. In this section, we will prove some of the properties of OLS estimators discussed in the previous section. The proof of others is beyond the scope of this module. Now consider the following simple heteroscedastic regression model where yi is equal to beta xi plus mu I, where I takes the value from 1 to n. Now variance of mu I given xi is equal to sigma I square, which is equal to sigma square into wi square, and I takes the values from 1 to n. Or the model is taken without an intercept and the dependent and independent variables are measured as deviations from their respective means. It is assumed that the variance of the error term is proportional to the square of a variable w whose values are known to us. It is also assumed that the model satisfies all other assumptions of the classical linear model, which is given by Ramanathan in 2002. Note that if we take a value 1 for all observations, we will have a case of homoscedasticity. The OLS procedure indeed assume that wi is equal to 1 for all observations and yields the estimate beta hat is equal to sigma xi yi upon sigma xi square into sigma hat square is proved to be equal to sigma mu I hat square upon n minus 1. Variance of beta hat estimate is equal to sigma hat square upon sigma xi square. This is our 13th equation. Now look at the proof of unbiasedness of OLS estimator of regression coefficients. So substituting for I from equation 11 into formula for beta hat, we get beta hat is equal to sigma xi yi upon sigma xi square is equal to beta hat is equal to sigma xi into beta 2 xi plus mu I upon sigma xi square. This is equal to beta plus sigma xi mu I upon sigma xi square. This is our equation 14. Since xi's are given and the error terms are assumed to have a zero conditional mean, we can show that expected value of beta hat is equal to beta. Hence, OLS estimators are still unbiased. Now, this proof requires only two of the assumptions of the classical linear regression model, namely the error terms have zero conditional mean and they are uncorrelated with the explanatory variables. Therefore, even if heteroscedasticity is ignored, OLS estimators are still unbiased. Let us now discuss the proof of consistency of OLS estimator of a regression coefficient. Since we know expected value of xi mu I equal to 0, by the law of large numbers, we can say that the probability limit of beta hat will be equal to its expected value as n tends to infinity. That is, probability limit of beta hat is equal to expected value of beta hat, and this is equal to beta, since beta hat is an unbiased estimator of beta. Hence, OLS estimator is consistent. Note again that this proof did not require any assumption on the variance of the error term. So, the presence of heteroscedasticity will not alter the consistency property of OLS estimators. Let us now discuss the proof to show biasness and inconsistency of variance of beta hat. From equation 14, we can write the variance of beta hat as variance of beta hat equal to 1 upon sigma xi square whole square into xi square into variance of mu I, which is equal to 1 upon sigma xi square whole square into sigma xi square sigma square wi square. Now this is equal to sigma square upon sigma xi square whole square into sigma xi square wi square. This formula takes heteroscedasticity explicitly into account. The OLS procedure that ignores heteroscedasticity gives an estimate of variance of beta hat as variance of beta hat is equal to sigma hat square upon sigma xi square. Now expected value of variance of beta hat all over the hat, which is the expected value, is equal to the expected value of sigma hat square upon sigma xi square and is not equal to variance of beta hat. The OLS estimator of variance of regression coefficient is thus biased and inconsistent. So look at the summary. The summary basically gives you the ideas we have enumerated in this. So in this module, we have discussed the nature of heteroscedasticity and its consequences for ordinary least squares estimation. We have learned that heteroscedasticity is a phenomena where the stochastic random disturbances exhibit a non-constant conditional variance. We have also learned that heteroscedasticity may be a result of specification errors or data issues. However, it is anticipated in most regression models with cross-sectional data, especially in cases where the scale of the dependent variable varies across observations. It is also observed in highly volatile time series data. Regression models involving time series data and dealing with values of explanatory and dependent variables that are of similar order of magnitude at all points of time are less likely to exhibit heteroscedasticity. In the presence of heteroscedasticity, OLS estimators and forecasts based on them are still unbiased and consistent, but they are no longer blue. The estimated variances and covariances of the estimators are biased and inconsistent. Hypothesis, testing procedures, and statistical inference are not valid anymore.